Yeah, thank you for giving me the opportunity to give a presentation here. So Guy has already sort of mentioned the title, Inference in Cardiac Mechanics and Hemodynamics, and really sort of motivated by our attempt to improve cardiovascular disease prognostication and risk assessment by making use of recent developments in the mathematical modeling of soft tissues, particularly sort of cardiac soft tissues. And sort of can we sort of improve our deepened methodological understanding to accelerate translation to get it into the clinic. In the first part of the presentation, I will be focusing on the left ventricle, that is the heart chamber that pumps blood into the systemic pathway. And the myocardium is typically sort of modeled as a soft viscoelastic material, which can be mathematically described by this strain energy function. So which describes how the strain energy changes in response to deformations, stretches along principal directions, in very simple terms, and that depends on various constitutive parameters. And these parameters capture sort of the stiffness and the elasticity of the material, and they are sort of potentially interest for biomedical sort of understanding. Now, sort of mathematically, then for the energy function by differentiation, get the forces, and you can solve these equations of motion subject to various conservation laws. And well, here's a paper by my colleagues in our applied mathematics group involving Xiaoyu Lu, Hao Gao, and Ray Ogden, who developed this mathematical model. The question is really, how do we get these constitutive parameters? So in principle, you can get them by taking the left ventricle, subjecting it to various amounts of shear in different directions, as indicated in this diagram, and then you measure the stresses, the forces. And the way I sort of see that or compare that with is what you would do with a spring. So the spring is one material parameter, that's the elasticity, and if you basically look at the force in response to compression or elongation, well, that tells you what that spring constant is, right? And for the heart, in principle, it's sort of similar, except that we have a three-dimensional object, and we look now at the stress response in response to different shears in different directions. Now, there's a small problem here, in that in order to do that, well, you need to get the heart out of the body, and that means it's not working in vivo. It's not useful for diagnostic purposes. So what we can do for sort of diagnostic purposes is magnetic resonance imaging. Right. And magnetic resonance images gives us information about the movement of the heart, of the deformations, but the information that we lose are the stresses, right, the forces. We have information about the deformation, but not about the forces. But that is not where our mathematical model comes in. So the mathematical model, if we know what the constitutive parameters are, that allows us now to simulate the kinematics. And here's sort of an illustration where we are looking at various circumferential strains in 24 positions on the epicardial wall, and these colored graphs show you sort of the evolution of the circumferential strains now during the pump cycle, going from systole to diastole and back to systole. And so that is what we can get from the mathematical model, but we also get that from the magnetic resonance images. Right? So we extract features from the magnetic resonance images. What my colleagues do is that they take a particular point in this pump cycle, that is end of diastole, and then they extract these 24 circumferential strains and the cavity volume of the left ventricle at end of diastole. Now, from the mathematical model, well, you can predict these features if you know what the parameters are. So you can match these features and look now for the best agreement, find the parameters that give you the best agreement. Quantify the mismatch, that gives you some objective function, then you optimize the objective function with respect to these constitutive parameters. Right. And so here's a paper by my colleagues. So what they did in an earlier study is that in fact, if you look at the mean square error between the different features that they extract, the 24 circumferential strains on the left, and then the volume has to be standardized, whereas the circumferential strains are already standardized. So just a sort of simple thing to optimize the parameters to minimize the mismatch. Now, the question is, what do we actually gain? So why are these parameters useful? Do they have really diagnostic power? And we did a simple case control study where we looked at 27 healthy volunteers and compared them with 11 STEMI patients. And STEMI is a particular form of myocardial infarction. And the question is, can we now well predict the disease based on these features? So what you typically want to do in a diagnostic setting is that you have the cardiomagnetic resonance scan. You want to make the risk prediction of developing a myocardial infarction. Typically we have sort of a team of medical experts who now envisage and look at these scans. That depends very much on their experience. So can we get a clinical decision support system to help them with the prediction? Any statistical or machine learning method can never actually work in the image space. The dimension is too high. What you typically do is find some form of dimension reduction. And what we want to do is, well, we use now the parameters, these constitutive parameters, as our sort of natural dimension reduction. And so we developed a Gaussian process classifier in this 8-dimensional parameter space of these 8 constitutive parameters. And then we got an out-of-sample sensitivity of 75% and a specificity of 95%. And that indicates that these constitutive parameters are useful for diagnostic prognostication, or risk prediction or prognostication of the disease. But there's a fly in the ointment here, and that is whenever you want to change the parameters, you have now to numerically solve your cardiomechanic equations. They have no closed form solution. What you typically do is use finite element discretization, but that is expensive. Now, if you think of these objective function measuring the agreement between the CMR scans and the prediction for the model, then you use some sort of iterative optimization algorithm, but whenever you change the parameters, you have now to run a forward simulation. You have to use another finite element discretization, which is expensive. And so the results from the previous study, they took us about over 2 weeks. And that means it's useless for the clinic, right? You can't use that for a clinical decision support system. So what we want to do with this, well, accelerate the process and approximate the mathematical model by a statistical surrogate model. So I call the simulator, that's the numerical solution of the mathematical model, and the emulator, that is now this the surrogate model. And work already has. There's some seminal work done by Tony O'Hagan, who's in the audience. That's, by the way, the paper from which I learned the method, your paper from 2001. And Richard Clayton's group, who's organizing this workshop, has done some pioneering work using emulation in the context of cardiovascular modeling. Right. So that's a very brief summary of the main idea. So here I illustrate that with 2 parameters, with 8 parameters, and 1 output. We actually have 25 outputs. But what you do is you cover the parameter space, and then you run forward simulations, and then you get now your output for these parameters. And if these parameters were discrete, then that would be the job done. You would now have a lookup table that giving the measurement, in that case the strain, you find the parameters. But because the parameters are not discrete, they are continuous, you have to fill in the gap, and that is where you use smooth nonlinear interpolation. And the method that we use is Gaussian process regression to now give us our surrogate model. Right. So that's basically the idea. Now, there are different emulation strategies. So here is again the objective function that we want to optimize. We've got these 24 circumferential strains, and then the left ventricle volume at end of diastole. So you can either develop an emulator for each of these outputs separately, right? So it's called output emulation, emulating in the space of the actual functions, or you could use an emulator based on the objective function, right? In which case you have less work to do because now you have a scalar quantity. Right? In order to compare these 2 methods, we covered the whole parameter space with 10,000 points from a space-filling design generated from a Sobol sequence. And then for all these points, we now forward simulate from the mathematical model, solving the finite element discretization equations. And so that takes in the order of 10,000 times 50 minutes per forward simulation, in the order of 100 days of CPU time. Obviously, you can parallelize it. But in terms of developing clinical decision support system, that is not a problem because you can do that in advance. Now, typically, patient comes into the clinic. Now you take the measurements, the circumferential strains, and the left ventricle volume at this reference point. Now you want to find what these corresponding parameters are. And so we mimic this process by continuing now the Sobol sequence for another 100 points. It's now an out-of-sample set that we haven't used for training. And then we want to see, well, how well we predict these parameters. Here we have the gold standard, because it's simulated, we know what the true parameters are. And here is a distribution of now the mean square error in parameter space out of sample for these 100 points. And you see sort of the distribution of the loss emulation, that is where we emulate the objective function, or the loss function, and the output emulation. And you see, well, you reduce the error by 3 orders of magnitude by emulating the output. And that is not surprising, because you obviously have more work to do here, because you've got the 25 outputs. But the interesting thing is to quantify the improvement, that we're not talking about a small improvement, it's a substantial improvement by 3 orders of magnitude. The other question then is, do we want to well, look at 25 separate univariate output GPs, or model the correlation between the outputs using the multivariate output GP? And use another of Tony O'Hagan's methods here. We look at the covariance matrix, and model that as the conical product of the output covariance matrix and the input covariance matrix. And if we then do the same analysis again and compare now the mean square error out of sample, we find again an improvement as a consequence of using modeling it at the multivariate output GP, which again is not too surprising, given that the different points on the epicardial wall are highly correlated, as you see that from the graphs. And so that obviously it makes sense to model that correlation structure. However, there's one thing that we need to consider. Training the Gaussian process and calibrating the hyperparameters, the length scale parameters, requires the inversion of a covariance matrix. And with 10,000 points, we'll have to invert a 10,000 by 10,000 covariance matrix that is of cubic complexity in the number of data points. And it also has sort of can have problems with numerical stability. So we want to reduce the number of points, so to reduce the complexity in the inversion of the covariance matrix and improve the stability. And so the various methods that have been proposed, I think the two mainstream approaches are sparse Gaussian processes and local Gaussian processes. I don't have time to talk about sparse Gaussian processes. I just focus on the local Gaussian processes, and that is a method suggested by or proposed by Gramercy and Apley. And the idea is simple, that if you look at the parameter space, well, you take the current parameter vector, then you find the nearest neighbors, and then you fit a local Gaussian process over these nearest neighbors. And the only problem here is that you have to reiterate that process whenever you change the parameters as part of your optimization procedure, which means you have to refit Gaussian processes then repeatedly, and that turns out to be computationally too expensive for the multivariate output GP. So what we did instead is, initially with some trepidations, thought, okay, let's not do the k-nearest neighbor fit in actually output in the parameter space, but in the output space. That gets around the problem of having to do the iteration. Now, you can think of scenarios where that might not work very well, but it seems that the objective function, at least for the cardiac mechanics of the left ventricle, is sufficiently smooth, so that in practice that was the method that worked best. And that was the method that gives us the best performance. So again, the distribution of the mean square error out of sample, and that is for 100 nearest neighbors. Now, where does that number come from? Well, initially we picked that on grounds of computational feasibility. So if you change k, well, you find that we can quantify sort of the deterioration that we're getting as k gets smaller and as k gets larger. So that is sort of a natural trend. But interestingly, we found that as k gets larger, suddenly the error increases and rather than decreases, which is initially counterintuitive because, well, how can an approximate model be better than the accurate model? So if you take all the neighbors, then you wouldn't have that approximation. And the reason is, we used, so where does that come from? We used a squared exponential kernel, that is a stationary kernel. We assume that the process is stationary, so using one of the standard kernels for stationary Gaussian processes. And it seems that, well, the actual process is not stationary, so you gain something by now fitting sort of approximating a non-stationary process by sort of local stationary processes. Obviously, that is something that one can improve. We're currently working on making the Gaussian process deeper and learning now the various hyperparameters themselves, either using Bayesian neural networks or Gaussian processes. Anyway, now let's get back to the real data. So magnetic resonance scans from a healthy volunteer, and here we don't have a gold standard, but what we can do is compare the results that we get with the emulator with those that we get with the simulator based on the true model. And again, that is the paper by my colleagues, where they use the original parameter estimation using the simulator at high computation costs. So given the parameters, we can now compute the Cauchy stress as a function of different shear directions. Remember, from the CMRI scan, you don't get the force, but the mechanistic model allows you to compute the force. And you see a comparison between literature, that is really what was taken from this paper based on the simulator, and the prediction that you get when estimating the parameters in the emulator. And there is hardly any difference. I mean, you have to magnify the difference by at least 2 orders of magnitude. If you then look at the residuals, you see that, well, effectively, for most parts of your stretch, there's no significant difference from 0, where these are actually, I have to admit, frequentist confidence intervals. Just for simplicity, we just used parametric bootstrapping. But the main achievement is that we brought down the computational complexity, which was originally in the order of nearly 2 weeks, down to less than 50 minutes. So that is where you actually get into the sort of time domain that you need to get the method into the clinic. Anyway, that was the left ventricle. Now let's switch to the right ventricle. The right ventricle pumps blood into the pulmonary circuit. And this is a project where we're interested in finding a way to diagnose long-term hypertension. Hypertension is high blood pressure, and it's a major risk factor for stroke, heart failure, and coronary artery diseases. Now, in the systemic pathway, it's straightforward to measure the high pressure. Right? You just use a sphygmomanometer. But you can't attach that to the lungs. So you can't actually get that into the lung. And interestingly, the blood pressure in the systemic pathway and the pulmonary pathway can be very different. I didn't know that before starting the project. So what state of the art is right heart catheterization. That is an invasive technique. It can lead to internal bleeding and also to a partial collapse of the lung. So for that reason, the ultimate objective is to find non-invasive alternatives for diagnosis of long-term hypertension. So here we want to model the blood flow in the pulmonary system, the pulmonary vascular network shown on the right, which you get from a CT scan. And we model the fluid dynamics. The fluid is modeled as a viscous, homogeneous, incompressible fluid. And the flow is assumed to be laminar, without swirls, and axisymmetric. So these are our model assumptions. And what is typically done is to map that 3-dimensional network onto 1-dimensional map. First, to bring the computational complexity down, but also sort of reduce the dependence on the initial blood vessel network structure. Then you can model now the fluid dynamics with effectively the Navier-Stokes equations. These are partial differential equations in the pressure and the flow as functions of time and the longitudinal spatial coordinate. The equations depend on geometry parameters like the blood vessel radius and the cross-sectional area. They are easy to obtain from CT scans, but you also have dependence on some constitutive parameters, not all of which can be sort of measured. The additional problem is that if you then look at the smaller blood vessels, at some stage you don't get them anymore from CT scans. The resolution isn't good enough. And what our collaborators do is exploit some similarities between fluid dynamics, so compliance, that is the increase in volume as a consequence of pressure, with a capacitance in an electric circuit. And so effectively the effect of the small blood vessels is mimicked, is captured by boundary conditions that depend on putting what's called a Wien-Kessel element, that is a small electronic circuit element composed of 2 resistances and a capacitor. Now the unknown parameters here are firstly these parameters, the 2 resistances and the capacitance of your electronic circuits. These are boundary conditions. They just mimic, they capture the effect of the small blood vessels. So you can't measure them, you have to estimate them. And then F, that's the stiffness parameter. That is the main parameter that is of interest for diagnosis of long-term hypertension. And this is a collaboration with a group of quantitative physiologists and mathematical modelers in Mette Olofsson's group at North Carolina State University. They've got data from hypoxic mice. So we have flow data at the inflow boundary condition, so that's what gets into the main pulmonary artery, and they get measurements of the pressure at position 1, that is the main pulmonary artery. And so see that for hypoxic mice and control mice. Now we want to do parameter estimation and uncertainty quantification, and we want to do that in a Bayesian way. We want the posterior distribution of the parameters given these data, well, the flow and the pressure profiles. And one way to do it is MCMC, although that's exactly what Chris discouraged to use. But you see that there's a practical problem here anyway, that if you say sort of curved manifold and run an MCMC sampler, then it might take 100,000 steps for it to converge. But here every step costs us a minute. It's cheaper compared to the cardiomechanic model, but nevertheless it's still a minute, and that gives you then a time of overall in the order of 70 days. So that is out of the question. So we thought of Hamiltonian Monte Carlo. Here the idea is that you introduce surrogate parameters, sort of equivalent to momentum terms, and then you get something that's structurally equivalent to a classical mechanical system, and then you generate what physicists call a canonical ensemble. That canonical ensemble is mathematically equivalent to the posterior distribution after sort of marginalizing over the momentum variable. So that is how it works. Here's the log posterior contour plot for illustration. You have a starting position. You draw now momentum variables from what's sort of a modified Maxwell distribution. Then you solve the Hamiltonian equations of motion. So this is a numerical integration scheme. Now you get a different point, but you conserve energy, so you can travel far and without staying in the high posterior probability area. And then you have a final correction step where you now use a Metropolis-Hastings step to decide on acceptance versus rejection. And that is overall much more efficient. You get larger effective sample sizes, but you now have two integration loops. You have the outer loop, where in every step you have to follow the Hamiltonian Monte Carlo trajectory, and that is a numerical integration with the Hamiltonian equations of motion. And in every single step, we then have to numerically integrate the partial differential equations, and that takes a minute every step. So that is not helping us. It's not bringing the computational costs down. And the idea is we want to get rid of the inner loop. Right? We want to eliminate the inner loop, and that is where the idea of emulation comes in again. So we want to use now the emulator for running these Hamiltonian dynamic equations, because now we can run easily sort of 100,000 steps of the Hamiltonian dynamics, because it doesn't cost us anything. We do not invoke the mathematical model, the simulator. The mathematical model is only invoked at the very last step when we do the Metropolis-Hastings step, so we have one numerical integration of the partial differential equations. So typically our MCMC trajectories have sort of 100 steps in that order of magnitude, and we only use one numerical integration. So that reduces the complexity by roughly 2 orders of magnitude, provided the emulator is a good representation of the simulator. The emulated likelihood is a good representation of the simulator. What happens if that's not the case? If that's not the case, well, the good thing is, mathematically, no problem. You still converge asymptotically to the right posterior distribution. What goes down is the acceptance probability. If there's a mismatch between these two surfaces, then the acceptance probability will be lower. So as opposed to the first part of the talk, where poor emulator gives us a bias, here mathematically we don't have a bias. We still have the guarantee to converge to the true posterior distribution. However, a good emulator is important for computational efficiency, not for accuracy. So that is a method that was first proposed by Carl Rasmussen in a publication in Bayesian statistics. But we have an extra problem to solve here. So I mentioned these physical assumptions of our fluid dynamics, and for certain parameters that's the case, for other parameters that isn't the case. So we can visualize that as, well, an area in the parameter space where sort of the blue area means that these parameters satisfy the constraints, and outside that area they don't. But the MCMC sampler is oblivious to that. The MCMC sampler can move outside the regime. If we're inside the regime, we put the parameters into our model, and yes, we get an output. If we're outside that regime, well, the program crashes. We run into singularity. We don't have any output at all. Right? And the problem is that we don't know where these boundaries are. If we don't know where they are, then we have to learn them. So what is the idea? We combine the statistical emulator with a statistical classifier. So formally, we've got a triplet of three numbers. We've got our input vector, these are our model parameters. We've got the output, these are the objective function, and then we have the crash indicators, binary indicators, and then we train two Gaussian processes. So the Gaussian process model to get the emulator, and the Gaussian process classifier to predict the probability of getting a crash. And then we can straightforwardly modify now your prior distribution by bringing the prior probability of being in a valid region in, and in that way modify your MCMC sampler. So let me now talk about the results. So again, these are the profiles, the data that we got from our collaborators in North Carolina. So the inflow boundary condition, that is the flow at for control mouse. Well, that's the study that I've shown now is for the control mouse and not for the hypoxic mouse. And then the pressure measured at position 1 at the main pulmonary artery. And so these are again the parameters of interest, 3 Windkessel parameters and then the stiffness parameter. And well, standard HMC has some tuning parameters, the number of steps and the step size. There are more advanced methods that we tried, so the no U-turn sampler, and then Riemannian manifold HMC and Lagrangian MCMC, as well as different variants of adaptive MCMC. And all these methods use Bayesian optimization to tune these hyperparameters. Not hyperparameters, the regular parameters for setting the MCMC trajectory, so epsilon L. And there's a plot of the posterior distribution that we get with the different algorithms for the 4 parameters, and they basically agree. There's not much of a difference. We also repeated the simulations for different emulators, because they all start with different Sobol sequence initializations, and that also gives good agreement between these posterior probabilities. So we have confidence that we've converged to the correct posterior distribution. So we can look at the computational complexity, so the effective sample size divided by the CPU time. And well, here it just turned out that NUTS, which does not use Bayesian optimization, was most efficient, that Bayesian optimization was in that sense sort of counterproductive, and that the computational costs were too high and you didn't gain enough. We can get now the posterior plots, looking at scatter plots of one parameter plotted against each other to understand the correlation structure a posteriori of the parameters. We can also get the marginal posterior probabilities. And you can take now these parameters, put them back into the model, then solve the model, and that is what we are now getting for the pressure at the main pulmonary artery, where black is the measurement, and then the red line, that is the posterior mean, and then the green lines, they give you the posterior credible interval, 95%. And you see, well, the credible interval is pretty tight, and although the fit doesn't look too bad, well, there's a significant difference with what we get from the model and what we get from the measurement. And one explanation is that we are missing out one source of uncertainty. We are looking at the uncertainty in the parameter inference, but we keep the vascular network structure fixed. Right? So there's some uncertainty in here as well, so we'll be looking into that. But there's also possibly a bias problem that that mismatch indicates deficiencies in the model, in that the fluid dynamic model does not allow for tapering in the blood vessels. We assume that the radius is always the same. We have to actually taper towards the end. And we also assume that we only have one stiffness parameter that applies to all the blood vessels. And well, actually, that could vary. So we're currently looking at a model where we give each blood vessel its own stiffness parameter, and then we introduce a hierarchical Bayesian model to sort of, well, a priori try to tie them together and penalize differences between them to sort of avoid problems with overfitting. But I mean, the main method is, or the main outcome is, that we reduce the computational complexity with standard MCMC, where you would naively solve the partial differential equations in each step of the MCMC simulation. It would be in the order of 3 weeks, down to sort of a computational complexity in the order of 2 hours to get an effective sample size of 1,000. And again, that is sort of moving closer to the clinic. All right, I think my time is now up. Let me just acknowledge my collaborators. The first part of the talk on the left ventricular cardiomechanics, most of the work was done by my PhD student Ellen Lazarus and my former PhD students Umberto Noi, Ben McDonald, and Vinnie Davis. The mathematical model was developed by my collaborators in the applied maths group, Hao Gao and Xiaoyu Lu, and the MRI data were generated in Colin Berry's lab in the pulmonary vascular and cardiovascular unit at Glasgow University. The second part on the fluid dynamics, most of the work was done by my PhD student Mireille Paun, and the mathematical model was developed by my colleague Nick Hill and our collaborators Mette Olofsson, Omar Kurushi and Mitchell Colbeck at North Carolina State University, who also obtained the data from the mouse study. The project was funded, or is funded, by EPSSC under one of these Center for Mathematics for Healthcare initiatives. And finally, sort of after this talk, you still have a chance to see the posters. Agnieszka Włocka, who was in my group, she has a poster on a similar topic where she is looking now at Bayesian optimization as opposed to emulation to infer the parameters of the mechanistic models. And that's it. Thank you, and time for questions.
Thank you for the talk. When you use the local GP strategy emulation for the emulation, do you think there is kind of a minimum in that mean error function as a function of k, the number of neighbors? Yeah,
in our case there is a clear minimum, but I think that is because the model is sort of misspecified. It makes a stationarity assumption, which is looks like it's violated in the actual function. And so you pay a price, you lose out, you have too much variance and uncertainty if the sample size is too small, but if it gets too large, then you're getting an average length scale, and you get a bias assuming stationarity where there's none, and then it pays off to have that extra flexibility by using that local GP. The question is to what extent that will scale up to higher dimensions, and probably with 8 dimensions that's still okay, but if you scale it up to higher dimensions, then sort of locality in a high-dimensional space can be quite misleading, and you might lose too much information. And so then it might be better to switch to the established sparse GPs. Yes.
The starting point you use is the one that gives you the best prediction for that specific output, right? When you start.
The starting point is driven by the optimization, because you have to do that. Well, if you do that properly, then for each parameter you have to find the nearest neighbors. What we did is, because it was completely too expensive, we looked at the k nearest neighbor in output space, which worked well, but possibly by a fluke. You can see that might go wrong, because closeness in output space doesn't necessarily mean closeness in the parameter space, but you do that only once. The data come in, you identify the nearest neighbors, because you've already run the forward simulations, you know what the nearest neighbors in output space are, take those, get the Gaussian process, and then you can do the optimization. And so at least for that study, it empirically worked well, and was the best method.
How much better is your partial network model than you would achieve with just a simple expanded Windkessel? I mean, so at the moment my worry is that you're actually you're only representing, in terms of the network, a fraction of both your compliance and probably very little of your resistance in the system. I guess you get some complexity there, but have you looked at just...
Yeah, that is a very good point. I mean, sort of what can happen is that you get sort of very good fit at the main pulmonary artery, and then you infer the parameters, and then you can also do the downstream projection, and in the smaller vessels, then you can get pressures that can be too high, that are physiologically not realistic. Also, you lose information with the Windkessel boundary condition. We also look at structured trees going then to larger generations, larger depth on the structured tree, which is certainly the better model in that it still brings the actual structure in, and then you average over the uncertainty. I think that's related to our first talk, sort of, what's an elephant? You want to have a complex model, and I think ultimately it's better to use the full structured tree, allow for the fact that you have the uncertainty in the the higher generations, so the smaller blood vessels, and then you average over this uncertainty. But the advantage of the Windkessel method is it also brings the computational complexity down.
Okay, I think we better break for the tea break, and back here at 12:30. Thank you very much.